In 2004, a massive retaining wall collapsed in Singapore, swallowing a 6-lane highway and claiming 4 lives. The tragedy wasn't just the devastating loss of life and millions in damages. It was the chilling realization that the engineers had sophisticated computer models and active sensors running right up to the moment of failure. The data existed to prevent the disaster, but the mathematical tools used to interpret that sparse, noisy data completely missed the reality underground. We tried to connect the dots using pure math, ignoring the actual physics happening between the sensors. How can we force artificial intelligence to obey the laws of physics so we never miss these blind spots again? Welcome to Strong Foundation Engineering. The Nicoll Highway collapse made this exact problem impossible to ignore. Monitoring data existed, yet the failure was never predicted. Every monitoring system in engineering faces the same fundamental problem. Sensors only give you numbers at a handful of isolated points, but the ground and the structure behave everywhere. Imagine trying to guess the shape of a massive ocean wave by only looking at 3 floating buoys. If you just draw a straight line or a smooth mathematical curve between those buoys, you are ignoring everything water actually does. That is exactly what happens when we use ordinary math to interpolate field data. We blindly connect the dots and assume the Earth behaves like a simple geometry problem. You might think modern artificial intelligence is the answer. Ordinary machine learning is fantastic at finding patterns and filling in the blanks. But here's the terrifying catch. Traditional AI has absolutely no memory of Isaac Newton, Henry Darcy, or Carl Terzaghi. It does not know what gravity or water pressure actually are. It will proudly hand you a smooth, highly confident prediction that completely violates basic principles like structural equilibrium or soil consolidation theory. It will predict that water flows uphill or that a beam carries load without bending, simply because the math looks pretty. It produces a confident answer that is physically impossible. This is where physics-informed neural networks, or PINs, change the game completely. Instead of just letting the AI guess based on data patterns, we bake the laws of physics directly into the training process itself. The network gets penalized not just when its answers mismatch the sensor observations, but whenever it violates the governing engineering equations at any single point in the domain. The physics isn't just a final post-processing check. It is the strict rulebook the AI must follow to learn anything at all. It forces the artificial intelligence to think like a civil engineer. Let's look at a concrete geotechnical example. Imagine you have sparse piezometer readings scattered across a massive earth dam project. If you feed those few data points into a pin that is mathematically constrained by consolidation theory, the AI reconstructs the entire pore pressure field across the whole site. It calculates how water is moving through the tiny voids in the soil, even in places where you have no sensors. What used to take weeks of tedious back analysis is now updated continuously in near real time as fresh readings arrive from the field. We map the invisible forces instantly. The same magic applies above ground. Consider an aging highway bridge. We can take limited acceleration data from a few sensors vibrating in the wind and combine it with the laws of dynamic equilibrium. The pin can mathematically reconstruct exactly where the concrete has lost stiffness or cracked, working backward from the vibrations. It finds the damage without a human inspector ever seeing it directly. It uses the physics of vibration to expose the invisible weaknesses hidden deep inside the concrete. Now, you might be wondering, does this replace the finite element method? Absolutely not. FEM remains the undisputed king when your geometry, applied loads, and material behaviors are perfectly defined. If you're designing a brand new building, you use FEM. But pins earn their place when your field data is sparse, your soil parameters are highly uncertain, and your model desperately needs to update itself from real-world conditions on the fly. FEM is for a perfect digital world. Pins are for the messy, unpredictable reality of a live construction site. But there's a massive trap here. A pin trained on the wrong physics will produce wrong answers with supreme confidence. If your assumptions about water drainage are incorrect, or if your chosen constitutive model misrepresents how the soil actually shears, the neural network will satisfy those incorrect equations perfectly. It will give you a beautiful, flawless answer to the wrong problem. In civil engineering, a low training loss on a computer screen is never a substitute for true engineering validation. The AI only knows the rules you give it. Pins are most powerful when the stakes are highest and time is shortest. Imagine a slope is saturating during a massive rainstorm, and a city needs to know right now whether to evacuate the neighborhoods below. That is not a hypothetical scenario. In Hong Kong, a system exactly like this exists and is running right now, using physics-informed AI to predict landslides before they happen. But AI is only as good as the physical data feeding it. How exactly do engineers gather that massive scale of real-time data to keep these systems alive? Find out in our next video. Subscribe to the channel and join our playlist to keep building your foundation.